Hi everyone, welcome again to the structural biology course. We are discussing structural biology techniques, more specifically X-ray crystallography, and today it is the last class of this long 3 modules of 15 classes, where we have discussed a lot of details of X-ray crystallography technique and associated parameters, associated instruments, associated things. So, what we are going to learn today is refinement. We will talk about refinement, we will talk about B factors, we will talk about occupancy, map development, R factor, simulated annealing, structure deposition and validation. So, from refinement I will talk about how you get a structure and deposit it, so that you are being ready to go for publication. Refinement target. Before that, you have to understand what is refinement. So, if you remember, we get our crystal, I am not going into details, we discuss about that many times. So, we have the crystal and now you do the diffraction experiment, you got a diffraction pattern, right. Now, from the diffraction pattern you get the F HKL, the structure factor, and rho XYZ, which is the electron density. So, structure factor and electron density. But we discussed here there is a big problem, which is a phase problem. You solve the phase problem by different way, one by direct method, then heavy metal replacement, and third, but definitely the best one is molecular replacement. So, with these you get a electron density, and with the electron density you have the electron density and you start developing the model. Definitely there are softwares which will help you to make automated build up of the model, but the tricky part is there are some of the portion where the electron density is not good. So, there what you have to do, you have to do manual. So, think about, it is not only about the theory, it is also about to understand the conception of how the things work. So, what you are doing actually, you have electron density and you manually put the amino acids, initially the backbone of the amino acid, the main chain of the amino acids, and then after that side chain. So, by your manual estimation you are putting the amino acid on the electron density, right. So, let us say automatic build up and manual build up of the model. So, when you are doing manual build up, you are making mistakes, which is natural, that is why it is manual. How to correct it? To correct it, what generally we do, this is called the refinement. What is refinement? So, what you do, you know the geometric parameters of the model. What I mean by that? By geometric parameter I mean you know the bond distances, right. Do not say no, because if you remember when we were discussing protein, we were discussing about the bond distances, bond angles, right, and very importantly torsional or dihedral angles, right. So, these are called bonded parameters. In addition, we are taking care of hydrogen bond, van der Waal and Coulombic interactions, the non-bonded parameters. So, what exactly is refinement? Refinement is you have all these parameters for amino acids, the standard ones. Now, when you are doing manual building, you make mistakes, and to check that you are making mistakes or not, in every cycle what you do, you run a energy minimization. What is energy minimization? I hope you remember what we talked about. Protein have a very complex pool. Pool means of potential energy surface containing the maximas and minimas. So, suppose you make a mistake, and for that the protein is now on the maxima or slightly upper to the minima or in a local minima. Now, if you perform energy minimization, there are many methods. I have also discussed the technicality of some methods. Here I discuss about simulated annealing, but I also discuss about other methods like Newton-Raphson, steepest gradient, steepest descent, conjugate gradient. So, I am discussing here the process of simulated annealing, but later in the molecular dynamics part of this course, the module, I am discussing steepest descent method, conjugate gradient method and Newton-Raphson method. So, in all of them you are providing a force in a force field with the parameters in the geometric library, and that would help the correction of the mistakes I make manually. So, if you see, refinement searches for a global minimum for a target energy function similar to the one illustrated, E total, the energy total equal to W X-ray E X-ray plus E conformation plus E non-bonded, which means or where the W X-ray is the weight for the X-ray energy term, E X-ray is X-ray energy term, E conformation is conformational energy terms or bonded energy terms, which talks about bonds angles, and E non-bonded is the non-bonded energy terms talking about van der Waals and electrostatic. So, there are different type of refinement. I am discussing the basic ones for your understanding, because as I told multiple times, this is a very introductory course. So, rigid refinement or rigid body refinement, what it does, it reduces the conformational freedom within the model to improve the ratio of observables to parameter in the early stage of refinement. What it is talking about? Suppose you are building up fingers of these two hands. Now, if they rotate between each other, you will get more probabilities, more degrees of freedom. So, if you consider them as rigid body, then you model the movement between them. That is what we are doing here. The entire model can be treated as a rigid body, or it can be regarded as linked rigid groups. If you see, there are two different domains. The one domain is considered as rigid body 1 and the other domain is considered as rigid body 2, and for each group of atoms specified by the user as a rigid body, the rotational and translational degrees of freedoms are minimized. So, what is the difference between rigid body refinement and normal refinement? In normal refinement, you allow every rotation and translation. Here, you are not allowing the rotation and translation of the molecules inside here, because you want to see the movement of one rigid body respect to the other rigid body. Coming to the positional refinement, the atomic position parameters x, y and z are refined for each atom. There are difficulties in protein crystallography. A large number of parameters have to be fit in the macromolecular crystals, especially which diffract weakly, producing a poor parameter to observation ratio. The geometrical constant introduced by the conformational energy terms, which are bonded terms, greatly reduces the number of parameters to be refined. Least square optimization or conjugate gradient minimization techniques are commonly used for finding the best fit of the model to the data. So, when we are doing a rigid body, it is relatively easier because you are not considering all the motions, and here we are taking least square optimization and conjugate gradient because they generally are less computer calculation intensive. Coming to B factor or temperature factor refinement, B factors are indicators of atomic mobility. High values correspond to low electron density, indicating a dynamic or disordered region or a possible error in position. Now, as in macromolecular crystallography or protein crystallography, we are dealing with a lot of things. So, unlike small molecule crystallography, it is very difficult to confirm you that which factor is actually influencing what. What I am trying to say? In general, if you consider B factor, high B factor says that there is flexibility or disorderness in the structure, but it might also be corresponding to low electron density. For a small molecule, it will never happen because the molecule is totally exposed, X-ray is diffracting, you get the diffraction data, calculate, you get a high B factor, you could be sure that this is because the molecules are moving. Not here, because here flexibility, but because of flexibility there would be low electron density, but low electron density could come by other factors which also could affect the B factor. The B factor is an exponential expression applied to the scattering factor that relates to the thermal motion of the scattering atom and the decrease in scattering intensity that results from the thermal motion. So, basically it is correlating to the thermal motion, that is why it is called proportional or correlated to flexibility. The formula is Fb equal to F e to the power minus b sin theta by lambda square, where Fb is the modified scattering factor with the B, the temperature factor. The X-ray energy term is modified in the target energy function is revised, where F calc is the calculated structure factor, is replaced by F calc stir with the refined B factor. So, if you look at here, scattering by a carbon atom expressed in electrons. So, because carbon have 6 electrons, so you see that it starts from here. Now, when you put this with different B factor, B equal to 0, b equal to 10, b equal to 20, the change in the angstrom 2 sin theta by lambda value. The B factor could be related to the mean displacement of a vibrating atom U by the Debye-Waller equation, which is B equal to 8 p pi square U square. B factor is calculated during structure refinement, describes local effect in electron density. If electron density is low, you will find high B factor. Unit of measurement is angstrom square. Higher the B factor, more imprecise the atomic position. Good protein structure is B factor within 20 to 30 angstrom. How B factor could be affected? B factor used to be affected with thermal motion, which I have already discussed, because with increasing thermal motion there is flexibility. When there is flexibility, the X-ray is hitting one time this position, other time this position. So, resulting low electron density or poor electron density. Different conformation of the side chain. If the side chain conformation would be different, then it would automatically fluctuate between A conformer to the B conformer, hence having a motion. Protein disordered, where protein is not getting very ordered structure like helix, beta sheet, it is having generally loop, that also flexible loop. Alteration of conformation, where there are change in conformation, and as I said, dynamic loops. This is, you will see the B factor map, and the values from blue to yellowish orange is showing low to high B factor. So, if you see in the core the B factor is low, whereas in the surface you generally see higher B factor, because in the surface the amino acid side chains, they are not getting interaction with the core. So, they are free, so they are freely moving. Because of free moving, they are creating high motion. They are, if there are disordered portion, they are also moving. So, it shows higher B factor. Occupancy refinement. The occupancy factor is used to describe movement of molecule in the model. An atom with a partial occupancy factor can be thought of as an atom that does not occupy that position 100% of the time. So, what it happens, occupancy is a very interesting subject. Why? Up to now I was talking about X-ray structure providing you very a static model, but considering occupancy you could see the alternative conformation. That means you could map the movement of the atoms, though the overall structure, overall result in the PDB is a static structure. Suppose we are talking about a tyrosine. If the tyrosine is having one conformer, the occupancy would be 1.0. But if the tyrosine have two conformers, then the occupancy would probably be 0.5, 0.5, but interestingly it might be others too. Also, here I have to tell you a very interesting concept. The software acceptance limits are there. So, it would consider the conformer up to certain level of intensity it is providing. What I mean by that? Let us say there is a tyrosine and it have 10 conformers. 5 of them would contribute let us say 0.01% each. And then there are 0.95, one is having let us say 0.9 or 0.8 and other 4 are having 0.04, 04, 04 and 03. So, 10 conformer 4, 8, 12, 15, 20, 0.8, 100, 1 I mean. So, you would be benefited to know the contribution of conformations, because might be some of the conformation which are not contributing higher stability might play an important role in development of the transition state, intermediates and all things like that. But the general trend of the software is to show that this conformation as 100% contributor. So, that is one, I would not say mistake, it is not a mistake, it is a limitation to the X-ray crystallography process. Some refinement programs do not require the occupancy factor be less than equal to 1. So, it is up to the crystallographer to remember that 1 is the upper limit on the occupancy factor for a given atom in a given position. We have already discussed about that. Occupancy is the fraction of molecules in the crystal in which a given atom occupies the position specified in the model. If all molecules in the crystal are identical, then occupancies for all atoms are 1.00. We may refine occupancy because sometimes a region of the molecule may have several distinct conformations. Refining occupancies provide estimate of the frequency of alternative conformations. If you see, so again before showing this data, I want to tell you one thing. We are discussing about structural biology techniques, but yet I have to introduce you about PDB. What is PDB? PDB is a format, it is called protein data bank, where all the biological macromolecules whose 3D structures are solved are deposited. I have to talk about that because that is one of the most critical part of structural biology, because whatever we are doing, the output would come in the format of .pdb format, which is a format where you get the x, y, z, the coordinates. So, here I am not going into details because I am spending few classes on this, but you will see that the x, y, z's are there, right, and this is the occupancy. So, you see this is a side chain of the arginine, and there is for one conformation 72%, which means 0.72, other 0.28, 28% conformation is 100. Again I just want to confuse you little bit, because this confusion will produce a creative mind in you. See, you have 1, this is 72%, this is 28%. How they go from one to another? Are you getting me? So, one is 72, another is 28, but in between the path there should be contributions, and that is what I was explaining. So, it is not about a perfect 72 and 28, it is like 72, 70, 20 in between several conformation contributing to the 10%. That is the general reality. So, after understanding this, do not say X-ray is only representing the static structure, X-ray is also giving clue to the dynamism of the structure using its occupancy as well as B factor. See two conformations showing occupancy. Here you will see, so one is having 0.5, one is having 0.5 or altering. Here also you see the difference in the positions they occupy. And also you could identify potential errors here, and you click and you check the occupancies, you could correct the maps. Application of B factor. If you plot the whole protein, main chain and side chain, you will see for sure more movement on the side chain. That is why you see that B factor residue number, you see higher plot, higher B factor for the side chains, because main chain is forming the core of the structure, they are more stable definitely than the side chains. This is comparison of a crystal structure with a built model. You see, even in most of the cases they do agree with the crystal structure, but at the initial few residues they show disorderness when it comes from the homology model structure. By comparing the B factor, it is one of the way to check the validity of a homology model if you have corresponding crystal structure present. More interestingly, simulation. As I talked about, in the simulation what we do, we have a force field and we develop force field parameter depending on what type of factors are influencing the biological macromolecule. For example, for protein we are taking bonded parameters which are bond distance, bond angle, which is bond distance, bond stretching and angle, bond bending and torsion. For non-bonded it is Coulombic interaction, van der Waals interaction and hydrogen bonds. When you do that, you find that which residues, like here nearly 100 you get a very flexible portion, most probably they are loops, and you could get to know the loops dynamics by applying MD simulation, but comparing the B factor from the MD simulation and crystal structure you could easily get the differences. Now I will talk about a very interesting validation which is called R value. In crystallography, the R factor or R work is a measure of the agreement between the crystallographic model and the experimental X-ray diffraction data. So, what you did, you get the crystal, you diffract, you get the diffraction data, the diffraction patterns, and you develop a model. Is there any disagreement between? Is there any error happened? R is a good measure of that. In other word, it is a measure of how well the refined structure predicts the observed data. You get a data and you have a refined structure, how well their coordinate could be estimated from the R value. The R value, which as I call R factor, R work, also called discrepancy index, residual factor or reliability factor, but generally it called R value. R value is a measure of the quality of the atomic model obtained from the crystallographic data. When solving the structure of a protein, the researcher first builds an atomic model and then calculates a simulated diffraction pattern based on the model. So, you know the diffraction happened, now you make a simulation diffraction pattern. The R value measures how well the simulated diffraction pattern matches the experimentally observed diffraction pattern. So, in one you are using the data making a simulation, in other you are using the actual data and you compare between them, that is R. A totally random set of atoms will give an R value of about 0.63. If you remember, you go back in the last class's slides and check, when we are doing molecular replacement, the R value was coming around 0.6 to 0.7. So, that is what a totally random set of atoms will give an R value of about 0.63, whereas a perfect fit would have been value of 0. So, you start from some point, you get the value of 0.6 to 0.7 range, but perfectly it should be 0, and practically if we compare the already solved crystal structures, it is around 0.2, but it varies with the resolution factor. Okay, we will talk about. In an R value, a fit may not be perfect for many reasons. One major reason is that protein nucleic acid crystals contain large channels of water. So, remember we talk about that in a crystal, a general conception is the protein molecule, the nucleic acid molecule, they freeze, and that is coming from the idea that we are getting a static model because the molecule is frozen there. But if you start understanding more about a crystal, especially protein and nucleic acid crystals, you will see that the crystal contain number of water channels. And I want to talk about a very interesting experience of mine as a experimental person. So, we always know the fact that in a crystal the protein is frozen, and if you see most of the protein, if they are structural protein, you do not have any assay to check that they are active or not. If it is an enzyme, it is difficult, because if you add A plus B to get C plus D, in the mixture there will be A, B, C and D. I explain a little bit. So, remember I told in crystallography, crystallization is a very critical part, we all discussed about that. Now, to get crystal, the crystallization process, one of the major challenges, it should be homogeneous. What that means? That means it would have protein. If it would have A plus B, if it is an enzyme taking care of the reaction A plus B to C plus D, if you add A plus B, there is a chance that A plus B react to make C plus D. If you know the general irreversible, non-irreversible nature of a reaction, what I mean, the reaction is generally reversible. So, what I mean, if A plus B makes C plus D, it is very rare that you will get 100% of C plus D from A plus B. So, what you will get? You will get, let us say, 25% A, 25% B, 75% C and 75% D. So, now if you imagine your active site of the protein, in one side there would be A and C competing, in other side you have B and D competing, and that would create a non homogeneous environment, and nearly it is impossible to get crystal in this situation. So, what to do? General strategy is to use what we call dead end complex. What is a dead end complex? A dead end complex is you use A and D or B and C, A and D and B and C, because you know A will never react with D or B will never react with C, neither they will compete for the same active site. This is called the dead end complex to use in protein crystallography. So, why I am talking about that? When we are doing that, it is out of your possibility to check that your protein is actually active or not in the crystal structure, because you have given dead end complexes. So, they are not anyway reacting. Fortunately, I was working with an enzyme called beta lactamase. I am still working on that. Beta lactamase encompasses one of the biggest problem in the field of antimicrobial resistance. It would sound like very non-scientific to say in that way, but if for any normal problem like headache to stomach ache, you go to doctor and 3 medicine you will get, you will check 2 of them would be beta lactam or beta lactamase inhibitors. So, these enzymes are very critical in understanding as well as in developing therapeutic measures against the drug resistant microorganisms. While working with that, I had the advantage with the fact that generally the substrate and enzyme, their interactions are non-covalent, as I described here. Fortunately, the exceptional case is with the enzyme beta lactamase. It covalently react with the substrate, and the reaction has 2 steps, acylation and deacylation. So, if one enzyme do the acylation and does not perform deacylation or being slow in their deacylation, we could trap the enzyme substrate complex. So, what I did, I wanted to use it to also understand the fact beside the scientific facts that in the crystal it would react or it would become unreactive because of the frozen nature of the environment. What we did, we crystallized beta lactamases, and in the crystal, when we soak the crystal with the beta lactam or beta lactamase inhibitors, to our surprise we find that they are attached with the enzyme in the crystal structure, meaning inside the crystal they react, and that kind of convinced us, and there are many other groups who are working on that, that the environment present in the macromolecular crystals are not frozen. So, that is what a major reason is, that the protein and nucleic acid crystals contain large channels of water. The water does not have a defined structure and is not included in the atomic model. Other reasons include disorder and vibration that is not accounted for in the model. There is one potential problem with using R values to assess the quality of a structure is the biasness. The refinement process is often used to improve the atomic model of a given structure to make it fit better to the experimental data and improve the R value. So, in the refinement process, that is the minimization process, it used to improve the atomic model which I talked about of a given structure to make it fit better. So, more you do refinement, it is like you put something inside a pipe and you move the pipe so that it could fit there, it is like that. When we do that, unfortunately this introduces bias into the process, since the atomic model is used along with the diffraction pattern to calculate the electron density. So, we get the information. So, in time of improvement a bias is included which affect the checking of the data further, validating the data. The use of the R free. So, up to now what we talked about R work or R value. In this moment it is a very significant understanding. So, listen carefully, we are introducing R free. The use of R free value is a less biased way to look at this. Why? Before the refinement begins, about 10% of the experimental observation are removed from the data set. So, now what I am talking about, this you will also apply when you are going to understand machine learning. Suppose in your school there are 1000 students. Now, you want to develop a machine learning program to find few features. Now, if you collect data from 1000 students and develop a model, now all of the students data is inside the model. So, if you use that model to predict anything about these 1000 students, it would always be perfect. That is called the biasness, because you have already taken everyone's data. So, what to do? To develop a better program, you need virgin data. What I mean by virgin data? By virgin data I mean your school have 1000 student. If you include 900 students data and keep 100 students data separate, make a model using the data from the 900 student and apply this AI based model, the machine learning based model to these 100 students, and you get good results, then you know your program is good. Similarly, what we do, we get the entire R value, and before the refinement we have taken 10% of R. So, we get the experimental observations, the frames, and we take out 10% of the data. Then refinement is performed using the remaining 90% data. The R free value is then calculated by seeing how well the model predicts the 10% that were not used in the refinement. For an ideal model that is not over interpreting the data, the R free will be similar to R value. Typically, it is a little higher. So, if you say 0.2 is the range of R work, 0.26 is the range of R free. So, mathematically how you do that? Measure of the crystallographic residual indicates the correctness of a model. R equal to summation of the absolute value of F ops minus absolute value of F calc by summation of absolute value of F ops. Variation that can prove confusing to the beginners are free, but you should not be confused because I talked about R factor for a test set of unique reflection that have been omitted from the refinement process to make it unbiased. There are two other R factors, R march and R sim. R march is the measurement of the quality of a merged data set when you are merging multiple data sets. R sim is the measurement of the variation between symmetry related reflections. Sometimes symmetry related reflections help us doing less work. Okay. So, what you have to remember is definitely R work and R free, but you just remember two terms, R merge and R sim. Merge is merging different data sets, sim is having a symmetry present. So, R free, R factor for a test set of unique reflections that have been omitted from the refinement process. I already talked about that. R equal to H scale to T with the same formula, absolute F ops minus F calc by F ops summation, where H scale to T designates all reflections belonging to a test set T of randomly selected unique reflections. The size of the test set is commonly 10% of the data set. Then we have R merge. R merge is the measurement of the quality of a merged data set. Again here 1 to n because different data, but then other than that it is same. Absolute F H scale is the final value of the structure factor amplitude for the set of reflection. N is the total number of data sets. As we talked about, different data sets are merging here. R sim is the measurement of the variation between symmetry related reflections. You see summation H scale with summation I is the center of inversion. We talked about F I H scale minus F H scale by summation of F I H scale. For I observations of each symmetry related reflections, where absolute value of F H scale is the average value for the structure factor amplitude for the I observation of a given reflections. I already told that I am not talking about simulation here, but one I think would give you at least a perspective. Simulated annealing is a MD based refinement technique that involves the control of the temperature mathematically related to kinetic energy of the MD simulation by T current equal to 2 Ke by 3 n Kb for n equal to degrees of freedom, Kb equal to Boltzmann constant. Gradient descent minimization and least square optimization methods are prone to get stuck in regions of local minima when applied to the first problem of solving the structure of a biological macromolecule. Do you understand? Let me talk about this. So, suppose we are talking about a protein. I talk about that there are different minimas, minima 2, minima 3, minima 4, other minimas there. Now, you can easily understand that minima 1, its energy is greater than energy of minima 2. So, minima 1, 2, 3 they are local minimas and minima 4 is the global minima. Simulated annealing is the process where you have to overcome those local minimas. Simulated annealing is mostly like our moms, our mothers. You are in class 10, you give a exam for the board, you get a certificate, happy. Your mom will say, what you will do in life? Go ahead. You will be irritated by continuous pushing, you go for 10 plus 2, finish, again push, go to engineering, go to general academics, from engineering go to job, go to MBA. So, how you are stacking a general nature of ours is to stuck in the local minimas, and we need someone like our mother to push us to go ahead. Simulated annealing do that. How? Let us check. In these cases, it is often necessary to overcome an energy barrier between the local minimum and the global minimum. Therefore, to reach the global minimum, an algorithm must be applied that can go energetically uphill. Motivation of simulated annealing. Motivation by the physical annealing process means heating process. So, it is a computational heat provider. Material is heated and slowly cooled into a uniform structure. Simulated annealing mimics this process. So, it provide heat and then go for cooling down. The first simulation algorithm was developed in 1953 by Metropolis. It could be compared to hill climbing. The main difference is that simulated annealing allows downward steps too. In the hill climbing you do not have downward step, but in simulated annealing you have upward, downward. Simulated annealing also differs from hill climbing in that a move is selected at random and then decide whether to accept it or not. So, there would be a random move and then you have to go for testing, I will talk about. In simulated annealing, better moves are always accepted, worse moves are not. Kirkpatrick 1982 applied simulated annealing to optimization problems. The paper is given here, it is published in Science. So, this is for your reference, you could check it. So, what is the problem of hill climbing? Get stuck at local minima, which we talk about. Possible solutions: try several runs starting at different positions, increase the size of the neighborhood, but then you have to choose the factor to accept or not to accept. The law of thermodynamics states that at temperature T, the probability of an increase in energy of magnitude del E is given by P del E, which is probability, exponential minus del E by kT, where K is a constant known as Boltzmann constant. So, as I told, to accept or not to accept simulated annealing, the steps P probability equal to exponential minus C by T greater than R, that should be the condition where C is change in the evaluation function, T is the current temperature, R is a random number between 0 and 1. So, you see there is a case study I have given where change is 0.2, 0.4, 0.6, 0.8 at temperature 0.95 and at 0.1, and you see the values of the exponential. You will choose only when it is the exponential of minus C by T would be greater than R. The probability of accepting a worst state is a function of both the temperature of the system and the change in the cost function. As the temperature decreases, the probability of accepting worse moves decreases. If T equal to 0, no worse moves are accepted, that is, you have to go for hill climbing. So, considering the condition of cooling, the cooling schedule is generally hidden in the proposed algorithm of simulated annealing, but it is extremely important. The algorithm assumes that annealing will continue until temperature is 0. This is not necessary for all the cases and could be modified according to the nature of experiment, nature of the macromolecule, nature of the experimental condition you are looking for. So, in simulated annealing, assumption the folded form is the minimal energy conformation of a protein. We use simplified energy function and search method for minimal energy conformation. So, use of simplified energy function which are easy computer, less computer intensive are steepest descent and Newton Raphson, and search method for minimal energy conformation is applying the method of simulated annealing. So, we are talking about, but what exactly is happening, I always try to give an example. So, let us say this is your protein molecule, it is stuck here, right, or here because this is. So, let us say here. Now, what you have to do, you have to take it out, you have to take it out from here. So, what simulated annealing does, it work by developing of a random number between 0 to 1, which will help. First of all, it provides a thermal energy, so that everything which are here, 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 they all go to up to certain energy level. So, these were there, I provide heat and they are here. Now, they are cooling down. How you know they are coming to a minima? First of all, you use that random number as a function and you perform dy dx. When dy dx equal to 0, you are confirmed that you are in a peak. It could be maxima, it could be minima, you attain a peak. Now, you do double derivative d2y dx2, that is greater than 0, less than 0, tells you it is a maxima or minima. So, first you know it is in the peak, maxima and minima both. Now, you confirm it is in the minima. Now, you calculate the energy. Suppose you get minus 5 kilocalorie. You repeat the process and in the next you get minus 7 kilocalorie. So, minus 7 kilocalorie means you are in a better minima than the other one. So, this one is definitely a local minima. You do not know this one is a local minima or not, you again do the cycle, and because you need to perform this cycle, we call it iteration. We apply a computational algorithm to perform this operation number of times, and at the end you see that in one minima you are getting where it is not from that. Even if you do a many possible runs, it is not going into lower minima. So, you know that this is the global minima. This is what I talked about in protein. So, I do not use model again, you already know the N-butane when you get to move the conformers, you get different maximas and you put maximas and minimas. See, this minima is lower than this. So, if this is local, this is global. So, as I told, global and local maximum, local minima, global minima, you get them, and this is the process I already talked about. So, how the cooling schedule would be maintained? First the starting temperature, then final temperature, then temperature decrement and iteration at each temperature, and the temperature choice will be made according to the requirement or setup of the experimental. Crystal refinement stuck into local minima. If you remember, I try to talk a details about the R factors. When you perform minimization in each of your cycle, you have observed there is minimization of the R. So, your journey starts at 0.6 to 0.7, 60%, 70%, and you have to achieve 0.2. Suppose in between, after multiple refinements, you are not being able to see the reduction of the R factor, you think that you stuck into the local minima. In that time, you have to apply simulated annealing to get out of this local minima and then continue. Also, peptide modeling, a lot of people do not understand, it is a very critical problem. Why? I want to explain little bit. First of all, why peptide modeling is coming very important nowadays. If you look at the therapeutic scenario happening, before people used to say it is the proteins which you should consume, and now the therapeutic spectrum is altering. Now people are saying it is not the protein, rather than the peptides. Your protein will go inside the body, your protein will be digested, it will be converted into peptide, and the peptide would be going and binding to the receptors to make certain things activated. So, peptide as a therapeutic agent, their requirements are increasingly coming up. What is the difference between modeling of a protein and modeling of a peptide? Remember, I told you have to imagine your protein. So, if you are blindfolded, your eyes are closed and you have a bowl in your hand and a string, and the bowl is filled up with 20 different color pearls. You pick up the pearls, you randomly put it on the string and you make a necklace. This is representing the primary structure. Then you try to make shapes and you keep making primary structure, secondary structure, tertiary structure and quaternary structure. Feel that when you are making shapes, they are coming together when they are not even together or close in the sequence. So, they have their internal non-covalent bondings and all, which is totally absent in a peptide. So, if my imagination of the blindfold experiment gives you an idea of a necklace, cut the small part of the necklace, makes a earring, and you will see the earring have much higher degrees of freedom in comparison to the necklace you made. That is the key of peptide modeling. A lot of people take the coordinates cut out from the protein and say that this is a model structure of the peptide. Not exactly, totally wrong. You have to take care of the increasing degrees of freedom of the peptides. So, that is why here is a peptide modeling algorithm which is taking the sequence, and then instead of doing long time MD simulation, it is doing minimization and simulated annealing by giving different initial velocities to different trajectories. Then it generates a large number of structures, and the whole structure assemblies go through the project screening, where about top 20% by ranking the value of residues in most favored region. So, you have all possible of them and you get the 20%. Now, you do the clustering and you get the largest cluster to be chosen as final conformation peptide. So, in that way simulation based peptide modeling would be used. So, we talked about refinement, now we talk about model building. The starting model we have through the molecular replacement. The initial model is the search model that has been positioned in the unit cell by the rotation and translation, as we talked about 6 degrees of freedom, 3 rotational degrees of freedom and 3 translational degrees of freedom. Anomalous dispersion isomorphous replacement model, which are coming from heavy atom. Electron density is calculated using the heavy atom phases, then the model has to be built into the electron density. Now, we will go for developing maps, electron density distribution. We know the formula. The first map is an approximation to the true electron density derived from the observed structure factor amplitude F obs, which is observed, and the estimated phases from the model coming from molecular replacement or heavy atom, where MAD, MAR, SAR, MIRA, CIRUS, every possible methods are applied. If you remember our illustrations, you would easily understand the fact that the correctness of the model image depends more on having the correct phase information than on having the correct amplitude. Remember the cat experiment, right? Cat and duck. Both tryptophans, if you see here, are from the same 1.7 angstrom crystal structures, but the map in figure 1 is the first map calculated using the initial molecular replacement phases, and the map in the figure 2 is the final map calculated using the refined phases. See, because it is refined phases, so here you get much better electron density map. Resolution limit is very important. 6 to 4.5 angstrom is placement of the secondary structures, 3 angstrom is for main chain tracing, 2.5 angstrom for side chain orientation, 1.8 angstrom for alternate side chain orientations, 1.2 angstrom for looking at the effect of hydrogen atoms. Map types 2 F0 minus FC map, F0 is observed structure factor, we talked about this, FC is the calculated structure factor. Subtracting FC from 2 F0 or F obs exaggerates the areas where F observed differs from FC. In the case where F0 is greater than FC, the net structure factor amplitude is intensified, and the case where the F0 or F observed FO is less than FC, the net structure factor amplitude is decreased. F0 or FO minus FC map, I used to talk about F0, but it is FO FC, produces positive or negative peaks in areas where FO differs from FC. This map is usually contoured at a high level. You get the contoured level by looking at the sigma value. So, all the crystallographer view are the large difference peak, not likely to be just noise. So, if you do in that way, you could see the actual electron density map and not the noise. So, now we have done everything. So, let us deposit the model in the protein data bank. So, you have solved your 1.2 angstrom crystal structure with an R factor of 15.4 and R free of 16.2. It is time to share your hard earned scientific knowledge with the rest of the world. When you publish your paper, most journals will request that you provide your PDB accession number. To add it on that, nowadays it is not only the PDB accession number, that there is a validation certificate coming from PDB. You have to submit that, only then the journal will agree to the fact that you have solved a structure. So, indicating you have deposited your coordinates for the betterment of mankind. So, then you go to the following website pdb.org, we will talk about. So, this is protein data bank, and PDB is the single worldwide repository for the processing and distribution of 3D biological macromolecular structure data. For deposition, you have to prepare data. PDB underscore extract, it is a resource which assembles specific details about your experiment and experimental model from your coordinate and structure determination output files in preparation for PDB deposition. SF tool, 1 to convert various structure factor format, 2 to check the model coordinates against the structure factor data. Ligand expo, formerly ligand depot, provide chemical and structural information about small molecules within the structure entries of the protein data bank. MaxSit assist in the processing and curation of macromolecular structure data. You also have to do validation. There are validation servers. This service is designed to help you check your model and experimental files prior to start of deposition. Information for journals. While publication of a related paper is not required for depositing a structure to the PDB archive, the release of structural data in the PDB at the time of publication is recommended. The WWPDB asks that journals provide the publication date and citation information for structure articles to make the publication of a report and the release of the corresponding PDB structure as simultaneous as possible. So, you deposit, it is there, then when you send the related work to the journal, when the journal will publish the paper, PDB will release your structure. Validation task forces, method specific validation task forces have been convened to collect recommendation and develop consensus on additional validation that should be performed and to identify software applications to perform validation tasks. I do not want to go, but this is a area which is very critical. If you imagine when the first crystal structure myoglobin was solved, people have never imagined that millions, at least like thousands of structures have to be deposited, but now that is the case. So, there are validation task force before you put it into format. Even when I was doing my PhD, I started my PhD at 2004. So, 2006 I have my first crystal structure. You deposit it, you have maintained the format, they give you a PDB ID. With the improvement and development of the fact that computational biology is dominating, they are using these structures. There are concerned that structures should be more corrected. So, there are validation task forces, X-ray validation task force, NMR validation task force, electron microscope validation task force. They are like a crystallographer like me is there in X-ray validation task force, a NMR specialist there in NMR validation task force. They look at other factors which the automation programs are not being able to detect, and they will send you again to improve those factors. So, deposit data www PDB one depth system, you have depositor ID, you have password, and you select the location of the institute of your PI, or if you are the PI, this will automatically direct to the closest PDB data center. RCSB PDB is for US, PDB-E for UK, and PDB-J for Japan. So, from where you are closest one, or you could also want to submit into certain place for faster response times for communication and computation. Validation suite, there are ProCheck, NuCheck, SFCheck. ProCheck I will talk about, assess the geometry of the residues in a given protein structure as compared with stereochemical parameters derived from well refined high resolution structures. Unusual regions highlighted by ProCheck are not necessarily errors, but may be unusual features for which there is a reasonable explanation. For example, distortion due to ligand binding in the protein's active site. Nevertheless, there are regions that should be checked carefully. So, you will give there, they will give you the report. The only input required for ProCheck is the PDB file holding the coordinates of the structure of interest. Now, practical considerations for resolution, like less than equal to 2 angstrom, for main chain conformation less than 3 angstrom, R factor, good upper limit for 2 angstrom data 20 to 23%, R free would be within 10% of the R work, and closer for the high resolution data. So, that is kind of it. This is a small movie, you could look how the change of resolution for a structure would differentiate the map, and how difficult it would be there when you are building up on a lower resolution. So, in summary, we have talked about cloning, overexpression, purification of crystal of protein. From there we did crystallization, from there we got crystal. We have talked about instrumentation and all. I will start the next module by discussing it in detail. So, we use the crystal for diffraction pattern. From diffraction pattern we get structure factor as well as phase in the structure factor, and so we have two components, structure factor and electron density. From there we have model, we have done refinement, then validate, and ultimately deposit the structure. So, that is a long journey of learning X-ray crystallography technique. I have tried my best to develop a continuous model so that you could follow me. If you have any questions, please keep posting. Thank you very much. Thanks.